The next topic in this course is using topological methods in combinatorics. And I'm not going to go very far into this topic, which is quite a big one, but I will just give a flavor of it by talking about a couple of applications of the Borsuk-Ulam theorem. It may not be completely obvious how the Borsuk-Ulam theorem could be used to prove combinatorial theorems, and that's what I will be showing. But in this video, I'm not actually going to give those applications yet. I'll be talking about just the Borsuk-Ulam theorem and some variants of it. I must confess that it's actually the second version of this video because I managed to give an entire, make an entire recording and put it up, which is now, I've now taken it down again, because I'd made a rather silly mistake that somehow affected the entire video, and in the end the best thing to do was just to re-record the whole thing. So here is the new improved version. So let me begin by saying what the Borsuk-Ulam theorem says, or reminding you, if that's, I would hope for most people that's the situation. It says the following. Let F be a continuous map from Sn, that's the n-dimensional sphere, which we could think of as the unit sphere in R to the n plus 1, to R to the n. So I said it was continuous. Then there exists x in Sn such that f of x equals f of minus x. Or to put it in a way that people like to say, f maps two antipodal points to the same point. I'll just write down for future reference what I just said, that Sn I'm going to be thinking of in a very concrete way as the set of all x in R to the n plus 1 such that the L2 norm equals 1. Right, now let's call that theorem 1. It's actually not the form in which we're going to be applying the theorem. In other words, we won't be applying this statement directly, but instead we'll apply a different kind of statement that turns out to be equivalent, but that is a bit more closely related to combinatorial concepts, and in particular the concept of coloring, which comes up in combinatorics quite a lot. So the first one that we're going to talk about is the following. Let a1 up to an plus 1, and my mistake in the last video, just in case you're curious, was I said a1 up to an, and that sort of threw everything, but a lot of the proofs somehow went through and I didn't notice that some other ones were not quite correct. So let them be subsets of Sn, and I'm going to assume that they're closed, and let's suppose that union of the AIs equals Sn. And I shall say slightly less formally, when the union of some sets is the whole of another set, I'll say those sets cover this set. So I'll say that the AIs cover Sn. And then the conclusion is that some AI contains a pair of antipodal points. Okay. Now what I'll do is prove that theorem 1 implies theorem 2, and theorem 2 implies theorem 1. So let's do 1 implies 2 first of all. So I've got my sets that are closed and that they cover Sn, and I want to define for myself a function from Sn to Rn that will help me obtain a pair of antipodal points in one of the sets. And I'll do that as follows. So define a function f from Sn to Rn plus 1, which is not quite what we want. And that's something that, again, that I didn't quite spot earlier on. We'll take f of x to be the distance from x to a1, distance from x to a2, distance from x to a n plus 1. Then f is continuous. But it looks as though we can't deduce anything, because theorem 1 only tells us about functions from Sn to Rn, and we've got a function from Sn to Rn plus 1. However, we're not in quite such bad shape, because what else do we know? Also, for every point in the image, or let's leave out the word for, so every point in the image has non-negative coordinates at least one of which is 0. So it's obvious that the coordinates are non-negative because they're all distances. Why is at least one of them 0? It's because we're assuming that the sets a1 up to an plus 1 cover Sn. And so that means every x belongs to one of the AIs, and then that coordinate, the distance from x to an AI that it belongs to, is 0. And therefore, every x has at least one 0 coordinate. So let's just draw a picture of where the image lives. I'll draw a sort of three-dimensional picture. So if we're mapping from S2 to R3, then we're going to live inside this plane here, and then the XZ plane, which I won't draw as well because it'll look, I'll try. So we're living inside that, and if we look at that from above, it basically looks like this. So when I say above, I mean kind of looking in at 0 down the direction 1, 1, 1. That's what we see, and therefore we can see that this set here is homeomorphic to R squared. And in general, so the set of all such points is homeomorphic to Rn via the orthogonal projection. So this is the, or a map that will give us a homeomorphism. To the subspace the set of all y in R to the n plus 1, such that the coordinates add up to 0. Well, it's a projection in the direction 1, 1, 1, 1, 1, 1, 1, 1. So therefore, now we've now mapped, if we compose with this homeomorphism, we've mapped to R to the n, and so therefore by the Borsuk-Ulam theorem, we can find x such that fx equals f minus x, and then we know that x is going to belong to one of these AIs, and so if dx AI equals 0, then distance from minus x to AI equals 0, because f is the same for x and minus x. So x and minus x belong to AI. Why did I use the fact that the sets were closed? Just here, from the fact that the distance from minus x to AI is 0, I deduced that minus x belongs to AI. And that wouldn't necessarily be the case if AI were not a closed set. Good, so let's now do 2 implies 1. So here, I'm going to assume, suppose that f maps Sn to Rn is a function, that's a continuous function, and that fx does not equal f minus x for every x. So that, just to make clear how the quantification works, for every x it is the case that f of x does not equal f of minus x. Okay, I'm going to use that to define a new function which I'll call g. So define g, but this is going to go from Sn to Sn minus 1 by, let's get a new sheet. We'll set gx to be f of x minus f of minus x. Now, one thing we know about f of x minus f of minus x is that it is not 0, because we were assuming that for no x is it the case that f of x equals f of minus x. So because of that, we can divide by f of x minus f of minus x, L2 norm. So that's a non-zero vector, so it's got a positive L2 norm, so we can divide by that positive L2 norm. And then we've got a vector of norm 1, so that really does belong to Sn minus 1. So recall that Sn minus 1 is the set of unit vectors inside R to the n. Now, Sn minus 1 can be covered by, let me get this right, by n sets nope, I don't mean n sets. This is where I've got to be very, very careful not to make the same mistakes as I made in the previous video. So that's n plus 1 sets with, also I want them to be closed, none of them containing a pair of antipodal points. Let's just see how to do that when n minus 1 is 1. So I want to cover S1 with 3 closed sets, and that's very easy done. I'll just draw an equilateral triangle. There are lots of ways of doing it, but I can draw an equilateral triangle. I'll take one set here, one set here, and one set here. I'm taking the closed arcs, so to speak, of closed intervals from this point to this point, this point to this point, and this point to this point. So I take a sort of big spherical triangle. And let me just say how I could do it slightly more formally in a way that will generalize to higher dimensions a bit more straightforwardly. So what I can say is I'll take an actual triangle, take an equilateral triangle made out of unit vectors, and I showed you how to do this in, well, in all dimensions in a previous lecture, previous video. And then I take each edge of this triangle and I sort of project it from the center out onto the boundary. And then if I want to prove that none of the images of these projected edges contains a pair of antipodal points, what I can do is I can say, let's take the vector that's not used in this edge, which is this one, let's say, and I'll take the plane, or in higher dimensions, hyperplane, or in this dimension, just a line that is orthogonal to the vertex that was not used. And then everything in this edge or face in higher dimensions, or hyperface, whatever, lies strictly in the hemisphere that's on this side of the hyperplane, and therefore can't contain a pair of antipodal points. So let me just write down something along those lines. To do this, take a regular, so we're in Sn minus 1, which lives inside Rn, so I've got an n-dimensional simplex. And take its n plus 1 faces, which are well, the sort of n-dimensional equivalent of, well, they're n minus 1 dimensional. I'll take those n plus 1 faces and project them centrally, so to speak, to the unit sphere. And I've taken the faces with their boundaries, and so these sets, that when I've projected them onto the unit sphere, are closed. So this gives n plus 1 closed sets. I'll call them, let's call them F1. F1 for face, and also because we sometimes like to use F for closed sets that cover Sn minus 1. And to see that Fi doesn't contain antipodal points, observe that the corresponding face of the simplex lies strictly to one side of the orthogonal complement of the vertex not used, or actually equals hyperplane through the origin parallel to that face. Maybe that's a slightly more direct way of thinking about it. So that's given us some sets that cover Sn minus 1, but I wanted to have n plus 1 closed sets that cover Sn, but I've got a function g that takes Sn to Sn minus 1. And something I meant to mention earlier, but I can mention it now, is that g has a nice property, which is that g of minus x is minus g of x. So let's go back to g. So g from Sn to Sn minus 1 is continuous. And for all x, we have g of minus x equals minus g of x. And so from that, it follows that the sets, so we've got n plus 1 of them, g to the minus 1 of Fi are closed. That follows from the fact that the Fi's are closed and g is continuous and do not contain antipodal points. That follows from the fact that g is an odd function. And just in case you can't see that in your head instantly, let me just quickly do that. So supposing we knew that if x and minus x both belong to g to the minus 1 Fi, then gx and g of minus x, which happens to equal by the oddness property minus g of x, belong to Fi, contradicting what we know about Fi. And this statement here, that g to the minus 1 Fi are n plus 1 sets that are closed without any of them containing antipodal points, precisely contradicts theorem 2. We were trying to prove that 2 implies 1, and what we've proved is that not 1 implies not 2. So we started with the assumption that we had a counterexample to theorem 1, and we ended up down here with a counterexample to theorem 2, and so that completes the proof of the equivalence. Right, let's move on to another equivalent statement. And that is actually the same as theorem 2, except we replace the word closed by open, but I'll write it out. So if A1 up to an plus 1 are open subsets of Sn that cover Sn, otherwise known as an open cover of Sn, then some Ai contains a pair of antipodal points. Right, so I'm going to start by proving that the theorem 2, which was the closed sets version of this statement here, implies theorem 3. So if we've got it for closed sets, we're going to get it for open sets. And I'll do that as follows. Let's define a function f. I'm just calling it f because there aren't very many letters for functions. It's got nothing to do with the f in theorem 1. So define f from Sn. Well, actually, first of all, it'll be more convenient to, for each I, define fi of x to be, or for each I and for each x, define it to be the distance from x to the complement of ai. And we'll also define that f of x equal the max over all I of fi of x. Now I'm going to claim that, well, first of all, let's just see that first thing, each fi is continuous. That's sufficiently easy to prove that I'm not going to do it right now. So each fi is continuous, so f is a max of continuous functions, or of a finite number of continuous functions is continuous. What else? So we also have that since the AIs cover Sn and are open, for every x there exists I such that x belongs to AI. Now if x belongs to AI, then because AI is open, it belongs to a little neighborhood, or into a little ball that is all contained in AI, so its distance from AI complement is positive. So there exists I such that the distance from x, well, such that x belongs to AI, and therefore since AI is open, the distance from x to AI complement is greater than 0. The distance from AI, x to AI complement was just fi of x, and therefore, so we get that f of x is greater than 0 for every x. But Sn is compact and f is continuous. So f attains its minimum, but it cannot attain 0, so its minimum must be greater than or equal to 0. Familiar argument. So there exists some epsilon greater than 0 such that for all x in Sn, f of x is greater than or equal to epsilon. In other words, f is bounded below by a positive real number. Now, what we were trying to do, we've got some open sets. We want to create some closed sets. And the idea is that when you've got your open sets that cover Sn, because open sets are open, they sort of have a little bit of extra stuff on the boundary that you didn't really need. And so we're going to sort of pull them in very, very slightly and take closed sets instead. We're going to just chop a little bit off the edge of each AI. That's the rough idea. So we'll define for each I, let bi be the set of x such that the distance from x to AI complement is less than, is greater than or equal to epsilon. That's a closed set. The quickest way of seeing that it's a closed set is that it is an inverse image of the closed set consisting of everything from epsilon up to infinity under this continuous function. We've just seen that for every x there exists an I such that this thing is wait a moment. Oh, sorry. We know that for every x, f of x is greater than or equal to epsilon, and that is equivalent to the statement that there exists an I such that fi of x is greater than or equal to epsilon. So we know that for every x there is some I such that the distance from x to AI complement is greater than or equal to epsilon, which is the same as saying that the bi's cover. So the bi are closed and cover Sn. Also, bi is contained in AI. Each I. Why is that? That's just because if x doesn't belong to AI, then its distance to AI complement equals 0, so it can't possibly belong to bi. And now we're basically done. So by theorem 2, some bi contains orbital points therefore the same is true of AI. So that's got us that the closed sets version implies the open sets version. And now we've just got one more thing to do, which is to prove that the open sets version implies the closed sets version. But actually we're going to do something slightly more than that. We're going to prove a mixed version. So here's the statement I want to prove now, or rather that I want to deduce from the open sets version, which is let A1 to AN plus 1 be subsets of Sn that are each either open or closed. And suppose that their union is Sn, or that they cover Sn. Then usual conclusion, some AI contains a pair of antipodal points. Right, so if they're all closed, then this will imply the closed sets version. So if we can deduce this from 3, then we've managed to prove the equivalence. But we're going to prove, so we're going to prove this by induction on the number of closed sets. Let's call it T. So if T equals 0, then we're done, because that's exactly theorem 3. That would tell us that all the sets are open, and we're assuming that the theorem is true for all sets being open. So otherwise, let's assume, without losing any generality, that A1 up to AT are closed, and that AT plus 1 up to AN plus 1 are open. So we'd like to prove that at least one of those sets contains a pair of antipodal points. So let's suppose that AT does not contain a pair of antipodal points. Right, so let's write it, just define a function and I'll sort of call it I'll call it f by f of x equals the max of the distance from x to at and the distance from minus x to at. Now, at doesn't contain a pair of antipodal points, so x and minus x can't both belong to at. So then for all x, because they're closed sets, if you don't belong, then you have a positive distance. So for all x, f of x is greater than 0. So then by compactness again, there exists an epsilon greater than 0, such that for all x, f of x is greater than or equal to epsilon. So that implies, so let's write at epsilon for what I think of as the epsilon expansion of A. So that's the set of all y such that the distance from y to at is less than epsilon. I would definitely want it to be a less than, because I'd like this set to be open, which it is because it's the inverse image of an open set under a continuous function. Then for all x, either the distance from x to at is at least epsilon, or the distance from minus x to at is at least epsilon. So we can't, so it is not the case. Perhaps that's going to be a bit sort of either x does not belong to at epsilon, or minus x does not belong to AT epsilon. So what have we achieved here? We started with the assumption that AT doesn't contain a pair of antipodal points, and I've managed to find a little blow up epsilon such that AT blown up by epsilon still doesn't contain a pair of antipodal points. But the nice thing about AT epsilon is that it's open. And so I think you can probably see that I'm now done. So let's just, by the inductive hypothesis, one of A1 up to AT minus 1, so only T minus 1 closed sets, and then AT epsilon AT plus 1 up to AN plus 1 contains antipodal points. And it's not AT epsilon, so I can just cross that out. So it must be one of the other sets. So what have we managed to conclude? We've managed to conclude that if AT doesn't contain a pair of antipodal points, then one of the other sets contains a pair of antipodal points. So in other words, we've got that one of the sets contains a pair of antipodal points, which is exactly what we were trying to prove. So that completes the proof that 3 implies 2. And that more or less completes this video as well. But I just want to mention one thing that may come as a slight surprise, which is that it looks very much as though this statement with mixed open and closed sets is a rather unnatural one, which you just bring in order to have a convenient inductive hypothesis. But actually, it turns out that we are genuinely going to use this mixed statement about closed and open sets for one of the 2 applications of the Borsuk-Ulam theorem in the next video. But for now, I've finished, so I shall stop.